So this is one more example where this is a massless pulley, spring constant K, string is idle, and over here the mass M is hanging over here. It has just been now supported, so that there is right now there is no expansion in the spring, and this is the natural length of the spring. So over here we have three reference diagrams we have drawn to find the time period of the oscillations. Now in this diagram we are talking about the equilibrium position, that is the mean position you can also say. So when this is gradually it is released, this goes down by a distance x. So that is, it has gone from this level through this level, it has gone by a distance x. If this has gone by distance x, then certainly this pulley will also go by some distance. So the pulley has gone from here to here, that is, it has gone by x by 2. When the pulley has gone from here to here, it has gone, that is x by 2 string, it has been released from here, x by 2 has been released from here. X by 2 has gone from here, x by 2 has gone from here, and where it has gone? This has vanished, this end is tied. So obviously this x by 2 and x by 2 that has been supplied to this end. As a result, this block goes down by x distance. Now this is stable over here. This is the mean position, everything is stable. We know, that is, if you remember what we did in laws of motion, we know very well, that is, if this is a pulley and over here in one string there is tension is T, in this string, that is the central string, it is T dash is equal to 2T. We know that, provided the pulley is massless. If the pulley has some mass, then you cannot use this, because that is, if we say this is T dash, ultimately this pulley is accelerating or not accelerating, doesn't matter, because mass is equal to 0, and let's say even if it is accelerating the upward direction, so equation comes out to T dash minus 2T, that is net force is equal to mass as 0 into acceleration. That's why T dash comes out to be 2T. So this is the one result we shall be using here. It means that T is here, in this it is going to be double the tension of this thing, or we can say whatsoever is the tension in this, it will be in this, and this it will be half of this. Now the extension the spring is x by 2. So the tension over here in this spring, we know that is, it is going to be a force into deformation spring, be it elongation or be it compression. In this case, there is elongation is there, and that is x by 2. So the tension in this is kx by 2. If the tension over here is kx by 2, in this and this it is going to be half, so it is going to be kx by 4. If we talk about this, kx by 4 is the upward direction, mg is in the downward direction. This is the equilibrium position, so that's why kx by 4 is equal to mg. This has been represented over here for this free, we have drawn a free body diagram for this pulley also, T, and this is kx by 2, so that's why 2T is equal to kx by 2, and T comes out to be kx by 4. For this, T is in the upward direction, mg is in the downward direction, so T comes out to be equal to mg. Kx by 4, T is equal to kx by 4, kx by 4 comes out to be equal to mg. Now we consider a case when it has been disturbed from its mean position and it is oscillating. It is oscillating with some amplitude. It is oscillating some amplitude, and we are talking about from here to here. We are talking about this. We are considering this position where it has some velocity. So this is not extreme position. So it means it will go even below this also it will go, and extreme position is going to be somewhere over here. This is the mean position, this is the extreme position. So over here it is going to have some velocity also. We are now talking of this position which is y distance below this. When this position we are talking about, which is y distance below this, over here it has some velocity also, and as it moves from this position to this position, that is y distance further below this level, so obviously there is going to be, once again there is going to be expansion in this. What is going to be expansion? We know if this goes by distance x, there is expansion is x by 2, the stretch is x by 2. Similarly, if we move it further by distance y, so this center of the pulley, from this level to this level, it is going to further move down by distance y by 2. So now the total stretch in the spring is x by 2 plus y by 2. That is the total stretch in the spring at this instant when the body is over here moving at the velocity v, and from the origin level it has gone x plus y distance below the origin level. So if we consider from here, this position to this position, the block has gone x plus y distance below this level, and this spring has stretched by distance x by 2 plus y by 2, and right now it has some velocity also. This block has some velocity also. So now we refer to the same diagram where now the extension is x plus y by 2 in the spring. This block has gone from its original position, it has gone down. That's why it has lost some potential energy, it has lost some height, that is x plus y, it has lost the height from its original position, and right now it has a velocity v also. Now we discuss about what are the gains or losses in potential energy and kinetic energy of the system. What are the transformations of energy which has taken place. This block has gone from here to here, so obviously this is loss in mechanical energy, that is mg x plus y. It has lost potential energy. And it has gained kinetic energy because at this instant it has some velocity, so the kinetic energy is half mv square. The gain in potential of the spring is half k, what is the total stretch is x plus y by 2. So the potential energy gain of the spring is half k x plus y by 2 square. Now we know that is because there are no distributive forces, there is no friction, etc. The oscillations, they are not damped. So all the losses is equal to gains as far as energy is concerned. So losses we have kept on one side, that is mgx plus y, that is the only loss. And over there we have these gains, that is kinetic energy gain by the block, and this is the potential energy gain by the spring. So in the next step we have just opened the brackets, and now we differentiate it both sides with respect to t. This should be t. This is t. With respect to t, we differentiate it. Now here one thing note is, that is this x is constant. This x is not variable. X is the distance when the body has gone down and it has achieved the equilibrium position. So this x is constant, whereas y is variable. Y lies somewhere between the mean position and the extreme position. This is any arbitrary distance. So dy by dt will give us the velocity, whereas the second derivative of y will give us the acceleration. So we used over here, as x is constant, so that comes out to be equal to 0. When we differentiate this, the expression like this comes, then dy by dt we have put it as equal to a. So we have used a simple differentiation concept we have used over here. So when we differentiate this comes out to be half m2v dv by dt, that is obviously acceleration. Over here if you see, that is mg is equal to ma plus k by 4 plus kx by 4. So it has both the things. It has mg also, this is, and kx by 4 also. So if you remember, when we had discussed the basic steps, that is how energy conservation method is used, over there to prove that is acceleration proportional to minus y, we may have some trouble, and over there we may have to refer to the how the equilibrium position has been achieved. This is what is meant by that. That is over here mg comes out to be ma plus ky by 4 plus kx by 4. So what we do is we refer to now the equilibrium position that was achieved over here. That is, in equilibrium position we know that is kx by 4 is equal to mg. We had just seen that. So what we do is now we put it over here. So as a result, this kx by 4 is cancelled by this mg. So as a result, we have acceleration is proportional to minus k by 4m by acceleration proportional to minus y, and from there it is shm, and then after that this is a regular kind of stuff we have been doing, that is t is equal to 2 pi y by a and t is equal to 4m by k. So this is how we can use the energy concentration method to find the time period or linear frequency. If we have to find the linear frequency, we can simply put it as 1 by t, and we can get the answer in cycle per second, hertz, or simply per second. We could also have got the same answer by using our regular steps, that is displace the body from its mean position by a small distance y, find the restoring force, find the acceleration should be proportional to minus y, then this t is equal to 2 pi under y by a. If we use that, we directly come to the equilibrium position. That is, this is equilibrium position. Once again, there is some extension, this x by 2 is extension this, and over here this has gone by distance x. So this pulley goes by distance x by 2. As a result, the extension this is x by 2. So over here in the spring, the stretch is x by 2. As a result, the force tension which is generated is kx by 2. The tension over here and over here is half of this. So the tension in this string comes out to be kx by 4. That is, kx by 2 is here, t is here, t is here. If we consider the free body diagram of this pulley is massless. So t plus t, 2t is equal to kx by 2, t is equal to kx by 4. And for this, t is here, mg is here. So t is equal to mg, because right now we are talking about the equilibrium position. That is, this body is not accelerating, and this is the mean position or equilibrium position. When the body has gone, this block has gone x units below its this initial level. So kx by 4 is equal to mg. So this is the equilibrium position. Now what we do is we displace this body by a small distance y, and now we are going to release it. So when we displace this body by a small distance y, we are holding it over here. So amplitude is going to be this much only. Amplitude is not more than that. We have just displaced it over here. So this is y. It has gone y further below this level x. So now from here to here, the total displacement it has gone as x plus y. But from mean position it has gone only y units below this level. When it has gone y distance below this level, so there is a further stretch in the spring, that is y by 2 is a further stretch. X by 2 had already been there. X by 2 had already been there, and now when we pull it by distance y, there is a further stretch of y by 2. As a result, the force in this, the stretching force, the tension in this increases further. Now T dash is going to be K, and total now extension this is x by 2 plus y by 2. So T dash is going to be, once again, if T is here, so T dash is equal to T. So T comes out to be 1 by 2, that is half of this going to be this much. And if we draw the force diagram of this block only, so T is upwards, mg is this way. When we release it, when we pull it here and release it, then certainly this will move up towards its mean position. So it means that is T dash minus mg is equal to ma. This T is what? This T is kx by 4 plus ky by 4 minus mg is equal to ma. So from here we get ky by 4 is equal to ma. We get a is equal to k by 4m into y, and that is acceleration proportional minus y, because what we have done is when we have pulled it over here, the displacement is in the downward direction, whereas the restoring force is in the upward direction, or the acceleration is in the upward direction. It means that is acceleration and displacement, they are opposite directed. If they are opposite directed, so acceleration proportional minus y, once again this is SHM, and T is equal to 2 pi, we get the same answer what we have got by the energy conservation method. If we hurriedly wish to find the time period without getting into much of the details, so this is how you can use it by energy conservation method, or by, let's say, understanding what are the forces which are acting on it, and then saying restoring force equal to mass into acceleration and acceleration proportional minus y. So from there we find the time period of the oscillations or linear frequency of the oscillations. Is there any other way, if we are in a hurry, to find what is the time period? Yes, it is. That says, that is, don't worry about that is how this equilibrium position has been achieved. This is purely, that is, we are talking about when we are just be bothered about the answer only. So over here we directly go to the equilibrium position. How this has been achieved is, we are over here, we are not concerned much about that is how the equilibrium position has been achieved. We are not bothered what is the stretch in this spring right now, or what are the forces which are acting on this block. Now we pull it by a further distance y. When we pull it by a further distance y, then as a result there is a stretch in this spring, that is y by 2 is the stretch in this spring. As a result, the force in this, extra force, we are talking about extra force, it comes out to be ky by 2. This is the extra force which is generated in the spring. When this is extra force ky by 2 is generated in the spring, over here we know that is half of this. So extra force which is generated in the spring is ky by 4. This is extra force which is generated in the spring. So what we do is, this is extra restoring force, and we directly put it as ky by 4 is equal to ma. We get the same thing, ky by 4 is equal to ma. Please understand, now we are not taking mg into consideration because that is not a fresh force. When we pull it by a distance y, we are purely bothered about the fresh forces which come into play. Now when we pull it by a distance y, we are looking for only for the extra restoring forces which come into play. mg was acting earlier also, mg is acting right now also, so this is not a fresh force. When we pull it by distance y, then extra force which generated over here is ky by 2, and the extra tension which is generated over here is ky by 4. We are looking for the extra or the fresh restoring forces. Fresh restoring force is ky by 4, ky by 4 is equal to ma, and we get the same expression because acceleration proportional to minus y, that's why it is SHM, T 2 pi y by a, and we will get the same time period as we have got by the earlier two methods.